So let's say you're working in art class one afternoon and you decide to draw the Olympic rings. Let's see if we can find the intersection points of these two circles. It appears that we have two intersection points. And so this may not be a perfect representation, but let's just act like the blue one is 8 sine theta and the yellow one is 8 cosine theta. Now, the period for both of those is pi. We know that because the typical period of sine theta or cosine theta on a polar graph is pi. So what we would want to do is graph the representation. And again, it's not perfect, but if we wanted to make it perfectly like this, that would take a lot of nasty rotations. Now, how are we going to determine where the two graphs intersect? So we can kind of look at the picture and we have an awareness that it looks like it's going to be at pi fourths for an angle, and it looks like it's going to be at 0. But the question becomes, how do we write these things in polar, and how do we make sure that what we're doing is correct? So the first thing you would do is you would set the equations equal to each other because both of them are equal to r. Then you'd want to solve for theta. So if you divide both sides by cosine, you get tangent of theta equals 1. So where does tangent of theta equal 1? That's at pi fourths. So that makes a lot of sense. So we have something, comma, pi fourths. And in order to find that value, we would have to plug pi fourths back into either of these equations, and we'd end up with 4 root 2. So we have the polar point 4 root 2 comma pi fourths. That's where those graphs intersect. However, we see that there's another intersection, and we're not getting that intersection by solving. The reason we're not getting it by solving is because these graphs don't actually intersect at that point at the same angle. And you should be seeing a picture, a rotating, moving picture on the left side of the screen right now, showing you that these circles, when we draw them according to where theta is, it never actually crosses this point at the same time. So they cross this point at the same time. When I'm drawing it and I'm moving at the angle at pi fourths, it shows up here. But in this case, the blue circle starts down here at r equals 0, whereas the yellow circle starts all the way out here at r equals 8. And so if I traced these, the blue circle and the yellow circle do intersect, but they don't intersect there at the same theta value. And that's why when you solve this, you never actually get a theta solution for the intersection at the pole. So we have this solution that we got with solving, but then there's another solution that we don't get from solving. We just have to realize that the pole can have different theta values for different types of drawings. So the blue one would be 0, 0, and the yellow one, it intersects the pole at 0 pi halves. You can continue to add whatever numbers you want to this for the angles. So the blue one would also intersect the pole at 0 pi and 0, 2 pi. The yellow one would also intersect the pole at 0, 3 pi halves, 0, negative pi halves, and so on. I could write this an indefinite amount of times since the period is pi. So I think it's important that we understand that when we're working with polar equations and polar points, there's many names for each point based on how long the radius is and what the angle is. So I actually could also have written this answer as 4 root 2, comma, 5 pi fourths, something like that. since the period of this is pi, I can just add pi and it will continually intersect at that point. So that's something to keep in mind. Typically when we write the answers to these things, we want to write them in a way that's easiest to get to between 0 and 2 pi. But sometimes it's actually beneficial to not do that. So for example, in this particular problem, we'll talk about an example where we may not want to write the answers in the way that I just described, but it's not horrible to do that. So I have the graph of r equals 1 and the graph of r equals 2 cosine theta on the coordinate plane. Then you set them equal to each other, divide by 2, and then you realize that cosine of theta equals 1/2 at pi thirds or 5 pi thirds. But you also could think of 5 pi thirds in the negative direction with negative pi thirds and pi thirds. I mean, there's an infinite number of ways to write these. We know that already. But the question is, what might be the best way to write the answer if I'm trying to do it in as little of travel as possible? And so if it says to write the answer between 0 and 2 pi, we would just use these angles. But if we want to think about how do I get the points to be in such a way where I'm traveling the least amount, I may want to use negative pi thirds and pi thirds. And here's why. Because on r equals 1, from negative pi thirds to pi thirds, that would be just a traveling distance and traveling amount of theta as 2 pi thirds. And likewise, on the blue graph, from negative pi thirds to 2 pi thirds, or I'm sorry, negative pi thirds to positive pi thirds, that would only travel around the circle like this. Whereas if I wanted to get all the way to 5 pi thirds, if I started at pi thirds, on the red one, I would go around this way. On the blue one, in order to find the intersection at the exact same theta value, I would have to go to here. Well, that's actually a 2 pi thirds on this blue graph. So then I would have to go all the way around again and then hit 5 pi thirds here. So you see how that's more of a distance for theta that it has to travel? Like these are a difference of 2 pi thirds, whereas these are a difference of 4 pi thirds. So this one might make a little more sense if I'm trying to minimize how far apart the thetas are. So here are my answers, but again, if it doesn't say how you have to write it, you could write this one as 1 comma 5 pi thirds if you wanted. I'm not going to be picky unless it specifically says which way you have to do it. So this is the answer, or you could write it in an infinite number of ways as long as it's correct. Let's say we want to determine the polar coordinates for the intersection of the same graph, except we're limited to 0 to pi. So notice that we only have one intersection now, and so it would be at the point 1 comma pi thirds. And how do we make sure that we get the r value correct? Well, you just substitute the theta back in to the original equations, and if I have theta values of pi thirds and 5 pi thirds, I just plug them back in. Now in this problem it's very easy because r equals 1 has to be true because the red circle always has r equals 1. But you can easily get the r values by just substituting them back in. Now this problem asks for the same thing with 2 cosine theta and 1, except from 0 to pi halves, so I have that graphed here, and again it's clearly the same answer. Now what if I change the problem to be the domain of theta is negative pi halves to positive pi halves? Well, I would graph those, and I would see that my answers are the same as I had on part 2a. If I changed the question to be between pi and 2 pi, I could graph those and see that my answer is 1 comma 5 pi thirds. So notice that these 2 points represent the same intersection on the coordinate plane, but if I ask for the answer in 2 different domains, for the uh, for the theta value, I would have to result or give a different result even though it's the same point. Finally, let's find the intersection of r equals sine theta and r equals 1 minus sine theta. So it's important to note that there's a different period for these things. So that means that the red circle will travel around twice in the time that it takes the blue circle to travel around once. So that's something that we have to be aware of. You set them equal to each other. You solve. You see that theta equals pi sixths and 5 pi sixths. Then you substitute these theta values back into your red and blue equations to see the correct answers. The other thing that we have to be aware of is if these fit in one period of sine, which they do, then the best answers would probably be pi sixths and 5 pi sixths because that's a pretty short interval of theta that it has to travel.